Sounds good. So hello everyone, you're tuned into today's PIR live event with Dr. Thamara Laredo, Assistant Professor in the Department of Chemistry and Sustainable Sciences at Lakehead University. My name's Anne, and today Dr. Laredo will tell us about her research that is helping to improve foods, such as coffee and chocolate, chemistry. So I'm really looking forward to learning more about your research and the possibilities of food science. But before we get started, I'd like to welcome today's viewers who are watching the live stream. It's great to have you all with us again today. For those who are watching the live stream, remember you can tweet your questions to us using the AskPIR hashtag. I'll be monitoring our Twitter feed throughout. And be sure to include your name or city so I can give you a shout out as well. So we'll get to some questions in just a little bit. But first, I'll turn it over to Dr. Laredo. Thank you so much for joining us today.
Thank you, and thanks so much for having me and for, I think this is a wonderful initiative, and thanks again for putting it together and organizing it. So my name is Thamara Laredo, and I work at Lakehead University in Aurelia. And I do a number of different things in research, but one of my main interests is in food. So in particular, I look at fats, and so among most of the fats that I've looked at, the idea has always been trying to replace fats that are known to be not so nutritionally desirable, such as fat and trans fats, and replace them for fats that have a higher nutritional value, like unsaturated or polyunsaturated fats. The problem, like any food scientist will tell you, is that you lose the sensory properties as soon as you switch a solid fat, like saturated fat. So, for example, butter. As soon as you make a cookie instead of butter with oil, then the cookie becomes oily. It doesn't have those palatable properties that you're looking for in a cookie. So just switching a saturated fat for a polyunsaturated fat is just not going to cut it. And just taking the fat altogether out of diet is also not going to happen, because we are evolutionary wired to enjoy fats. So we can't just cut it out. It's too much of a lifestyle change, and people are not in for that. So one of the things we're trying to do is, how do we substitute these fats for more nutritional ones without changing the properties of food or of food products. And one of the things we found is that you can take, for example, oil. So this would be your liquid, sorry, because the camera shows right and left, so I'm a little bit confused as to what is right and what is left. This could be liquid oil. So this is high oleic sunflower oil. And we can gel this into something that looks like, where am I? I'm looking at all my little jars. Something that more or less looks like this, and actually this is not quite gelled, but we can definitely gel it and make a solid. This, for example, here is a gel that you think is fat. It's just fat. It's sugar and a polymer, which is ethyl cellulose, which is a derivative of cellulose. And cellulose is paper, basically. It's the most abundant polymer in the world. And so it's a form of cellulose. It's not quite cellulose. It's food grade, and we gel it in the presence of fat. And here there is also in the presence of sugar. And so you end up with something that is quite solid-like. So basically, the idea is to use this in food products to, now you're using a liquid oil, but it's been gelled, so the properties are almost like solid-like properties. And it is an unsaturated fat. So in principle, it has a higher nutritional value than a saturated fat. And plus, you get rid of all the health disadvantages. For example, saturated fats are shown to increase cholesterol and obesity also, and never mind, trans fats are even worse, right? So the idea goes along those ways. And also we do some research on other things. We've looked at coffee, and we're actually doing some more research into the coffee area, and I can talk about if there's questions, but I think that now maybe it's just good to just with what I've said. We can just go over questions, or I can show around. I'm in the lab right now, so I can show you guys if people are interested in what the what's that?
Oh, I just said, yeah, let's see your lab. I'm interested sort of in what tools or techniques you use.
Yeah, so this is a Fourier transform infrared spectrometer. We have different attachments we can use with it, and it's interfaced into a computer. And I can talk about how it works, but basically what we do is there's a beam that comes out of here of infrared light, so we can't really see it. There's a laser too. There's the laser. Do you see the red dot in my hand? So that laser just goes to show you where the infrared beam more or less is. Infrared is non-invasive, so it's not that I'm going to lose my hand by putting my hand over there. This is very low power. And so the sample goes here, and it goes into a detector that goes here, and so basically I can get their identification of what the compound is, but usually I know what the compounds are because I prepare the samples, but I can understand that, for example, the interactions of things that are happening at the molecular level, or I can also quantify, depending on what the sample is, of how much of one fat there is with respect to another fat if I didn't make the sample. But most importantly, I can understand, for example, when I showed you that gel that had fat and oil and, oil and the polymer, the cellulose polymer and sugar, I can understand why is this thing actually gelling? Like what is happening with the molecules that there is an actual interaction that is holding my gel together. Because you think it's anything, it's Jell-O, it's toothpaste, it's hair gel, anything can be a gel, but all those gels are aqueous, right? All those gels are gels in which the liquid phase is water or a water solution. When you make Jell-O, you're just adding water to a powder and you make a gel, a very hard gel. Here we're doing the same thing but with oil, and the interactions are not as easily understood or as well understood, and it's not as straightforward as when you have water. So this is the main equipment that we use to understand that. How we do samples and how we have two ways. We can do transmission, which would mean that the beam goes from here to here, and it goes through the sample that would be sitting here, and that is transmitted light. Or we can do reflection. And what this is it's an attachment that has a number of mirrors. So the beam goes in this way, and then there's mirrors that reflect the beam all the way to the top of here where I'm going to have my gel or my liquid. And so the beam is reflected up and down, and then it's collected in these mirrors again and comes right out. And this whole attachment goes in here, and so it goes right into the detector, and I can measure. So there's two ways I can measure things. And again, there's lots and lots of things that we can talk about, but I think maybe now it's a good idea to maybe take some questions from the public.
Yeah. So I'm still waiting for a few questions to come in on Twitter. Remember to tweet them with hashtag AskPIR. But I actually have a question for you, going back to I forget what you called it, that machine that has the laser. So what was it called again?
It's an FTIR, so people know it by the acronym, which is FTIR, and it stands for Fourier Transform Infrared, and it's a spectrometer. It's basically a spectrophotometer. So the response of the machine is a spectra, it's a graph. I'm actually going to pull one up as we speak so that you can see what it actually looks like, and we can take a spectrum right away. So when I'm going to put the camera. Okay, so here we are in the computer, and I can just say, okay, so we're going to collect, let's just collect a new background or a new sample, it doesn't matter. So right now it's just collecting the spectra of air because there is no sample in the sample holder. And so this is what it will look like. This is what it looks like. So what you have here is a signal of the intensity of light for all these wave numbers, which wave numbers is a way of expressing wavelength. So here we're talking infrared, so we're in the order of microns. So it's a wave, so it's not the laser. The laser just is a guide for us to see where the infrared beam is, and it also provides a time guide. but the actual beam is infrared, which is heat. So if I put my hand here, which is where the lamp is under the plastic, it's actually a little bit warm because the infrared is just heat. Any source of heat, when you have your stovetop on and you see it glowing red, the heat that you're feeling is infrared radiation. And so that infrared light is just basically it has a defined range of wavelength, which we can express in wave numbers, and it's more commonly expressed in terms of wave numbers. And then, so this is basically the intensity. And I can, for example, what I was doing here before, if you have, here we were taking samples of some sort of milk. And what we can do is we can ratio a sample over a background or a blank, and when we ratio that, we get something that looks like this, and if I make it look like this, this is basically what a spectra looks like. So I'm just going to put it in a new window, and it looks like something like this. So what we're looking at here is the absorbance. So how much light is my sample absorbing with respect to no sample in the past? And these bands here correspond to molecular vibrations. So this corresponds to the vibration of a certain group of atoms, and this corresponds to the vibration of a certain group of atoms. And so when I compare this to, for example, another sample that has something a little bit different, then I can make correlations as to what kind of molecular vibration or molecular interaction is happening in one that is not happening in the other. And that allows me to make inferences as to what the molecular mechanism of a certain phenomena is.
Okay, cool. So basically your process might be to analyze, a natural piece of chocolate, something that has saturated fat, and understand that, and then determine what changes molecularly need to be made?
Yeah, we can, for example, we can look at, why, I can't tell you, for example, why chocolate tastes so good from molecularly speaking, but I can tell you, for example, that the fat in chocolate, which is cocoa butter, behaves in a certain way, and it has to be crystallized in a certain way, and I can tell you molecularly how the cocoa fat is so that sensorially you get the best experience out of chocolate. And so then I would like to main thing is an gel.
Very cool.
Does that make sense?
Yeah. So we have some questions coming in now.
Super.
Mel's wondering, how long does it take for the FTIR to determine the makeup of a compound? Is it instant?
You saw how fast we took a spectra. So the spectra depends on, if you have a lot of samples, then you don't need that many spectra. If your sample is extremely small, like we're talking under micrograms, it is extremely, extremely small, then you have to collect the spectra for a long time. The collection of the spectra is not the problem. The problem is that the bands that you get are not unique. So a certain grouping of atoms will always show the same signature in IR. So for example, I'm going to flip the camera again. For example, these peaks here are correspondent to a certain grouping of atoms. And as long as I have molecules that have this grouping of atoms, this will show up. The thing is that if I zoom in, for example, this may be a little bit shifted to one side, or it may be a little bit wider, or this may be less prominent or more prominent. So the collection of the spectra is not the hard part. The hard part is interpreting the data and figuring out what is going on here, because just by looking at it, all I can say is that there's a certain grouping of atoms that are present in the molecule. And I knew that to begin with because I know what the molecules are because I put them there. Does that clarify?
Yeah. Another question about the FTIR. Do you need any special training to use it?
Yes, absolutely. You can't just come and use it. I mean, it's pretty, when you look at it, it's pretty black box thing. Like there's no buttons basically in it. Like this closes down and then that's it. This is just a little piece of metal that we have here. So there's really no buttons in it. These are not buttons. These are just lights. These are some connectors. So in case you want to expand. what can the PIR do, and there is really just 5 buttons, which in reality, these are hardwire buttons, but you have access to them through the software. So if you come, you put a sample in, let's assume that you know how to put a sample in here, and you take a spectrum. Again, that's not hard. That is quite easy. The problem is to make sense of what you just did. So there is a lot of training, especially depending on what you want to do with the IR. The IR can do absolutely anything you want it to do. I mean, right now I'm looking at food, and I looked at caffeine content in chocolate using the IR. I've looked at pollution in water samples. I've looked at a number of different things. I did my entire PhD on cell membranes and understanding the behavior of proteins in cell membranes within the IR. So it can absolutely measure everything, but in each way you're measuring things, you're doing it in a different way, and you're taking different considerations, and that is something that one needs training in. It's otherwise you're just collecting the spectra, but you have no idea what to do, and you don't even know if you're collecting the spectra the way you should be collecting it.
Right. So what sort of information are you collecting when you study coffee? Are you putting coffee into the FTIR?
Yeah, so it can be done in different ways. So what we wanted to look at when we did the coffee study was we wanted to figure out the caffeine content. How did the caffeine content in brewed coffee, not in grounds, but in the already brewed coffee, how much did it change if I changed the grinding time of coffee beans? So there were a number of studies that had already been published, and they were all qualitative, and they would divide the caffeine content into fine ground and coarse ground coffee. But we actually timed the grinding, and so we did from beans that were whole without any grinding to grinding we went up to ridiculous times like 80 seconds. And what we found is that when you extract the caffeine, and that's where we use the TIR, is we extracted the caffeine, we put it in this trough here, and then we measured it for each of the brewed coffees. And what we found is that, the more you grind, as you would expect, the more you grind, the more caffeine you get out of your beans. But the interesting thing is you can actually, if you grind for around 40 seconds, you get twice as much caffeine as if you were to grind for 10 seconds, which is usually when you buy a blade grinder, what the manufacturers recommend is between 5 and 10 second grinding of the beans. And if you grind 4 times as long, then you will get like up to 40 seconds. You get 100% more caffeine, and that was quite surprising quantitative results. If you grind past 40 seconds, there is no change, so there's no point in going as far as 80 seconds. But we needed to do it in order to figure out that there was no change. But so the way we did it is that, so in that case, I didn't do transmission. I did this type of experiment, which is reflection, basically.
Yeah, cool. So that's a really cool discovery, and also good to know for maximum caffeine.
Absolutely. We've had a lot of people. We present work in scientific conferences and also to the public, and people's response are very, very warm. People are they relate very much to the idea of caffeine in coffee, right? I mean, some of us just like the taste. Like I think that in my family we're all immune to the caffeine. Like I could have a coffee at midnight and it won't keep me up. I just like the taste, but some people are definitely in for it for the caffeine. So knowing that is it's also important. For example, if you're in a caffeine restricted diet and you think that you're okay taking 1 cup of coffee a day, but the reality is that it has to do with your grinding. If your cup of coffee is made from beans that have been ground for 40 seconds, you're taking 2 cups. So it's interesting in that way too.
Yeah, absolutely. So on the topic of discoveries, have you made any other sort of unexpected discoveries?
Well, we're looking now into roasting times, and we're working with green coffees, and so we're on our way to like figuring out a bunch of stuff. But so far, in terms of things that are practical like that, I think that so far that's one of the bigger ones. But yeah, I mean, we've been able to, in terms of the chocolate, we've been able to actually the whole idea of just gelling oil. It's the idea of gelling oil is not new. The idea of gelling oil with a cellulose derivative is quite new, and that has huge implications because normally gelation of oils happens with very small molecules that are added into the oils, and that changes the taste properties. A lot of these molecules are not food grade, so they can't really be used in the food industry. But ethyl cellulose is safe, FDA approved, food grade, and so that was a huge thing too. But that was work that has been years in the making. It's like it's work that I do in collaboration with researchers at the University of Guelph, and it's been going on for 6 or 7 years. It's been 6 or 7 years of work that now we've been able to say, okay, we can gel these things, and not only we can gel these things. Actually, when you put ethyl cellulose in chocolate, you end up with a property that is extremely desirable in certain markets. It's a property of heat resistance. So it's basically chocolate that doesn't melt. So it's like the chocolate that melts in your mouth, not in your hand, but without the candy coating of M&Ms, right? So that was quite a discovery, the heat resistance effect, and it is a sought after property for producers of chocolate in tropical countries and really, really warm weathers, because otherwise you can't have dark chocolate. Dark chocolate melts faster than milk chocolate because in principle it's not supposed to have milk. So it allows it to, like, it doesn't allow it to be very heat resistant. And so the fact that we now can produce a chocolate that has quite a resistance to heat was an interesting discovery, and we've studied it at length as to why this happens, the molecular mechanism as to why this happens.
Yeah, that's really cool. So we have another question that's come in. Drew wants to know, chemically alter chocolate to have a different color. So could you analyze it in the FTIR and sort of figure out how you could change the color?
Well, as in like you go to the bulk barn and you find green chocolate and pink chocolate. Yeah, I mean, that's just a color additive. The news that people don't know is that is not technically chocolate. It has to do with the regulations of what we can call chocolate in Canada and what we cannot call chocolate. So, for example, if you buy a Snickers bar, you will see that it says candy. It says Snickers, and then right underneath Snickers in small letters it says candy. And the reason is because it cannot be called chocolate, a chocolate bar, because even though it has cocoa butter, it also has palm kernel oil, which is a saturated fat, which is meant to substitute more or less some of the cocoa butter. And so as soon as you put palm kernel oil or coconut oil or any sort of vegetable oil to try and substitute some or all of the cocoa butter in a product, it cannot be called chocolate anymore. So when you
Oh. We'll just wait a minute. There's a few minutes left in our event today. We'll see if she can join back on. I wanted to ask her if she had any advice for students who wanted to pursue a career in chemistry or food science. Let's just see if she comes back.
I don't know what happened.
That's
It
okay.
just died. All of a sudden, yeah,
I'm sure it
all
was
of
the
this
Wi-Fi.
connected.
I just wanted to ask one
Yeah.
more question for you.
Yep. Yep.
I was just wondering if you could talk a little bit about your career path and maybe if you have any advice for students who want to pursue chemistry, food science.
Absolutely. I'm from Venezuela. I'm originally from Venezuela, which is a Spanish-speaking country. So if you hear a little bit of an accent now, you know why. And I did my undergrad in chemistry in Venezuela, and then I wanted to do a PhD, so I went to the University of Guelph in the chemistry department, and I did my PhD there. And then I worked at the molecular level for a long time, and I wanted a bit of a break, and I wanted to work with things that were on a larger scale. That's why I went to food science. Little did I know that I was still going to look at molecular behaviors, but of samples that were much larger. So I would actually be able to see the sample. For 5 years, I worked on things that I half the time didn't know if the sample was there or not. So I set the food science for a year as a postdoc, and I got hired at the university as an assistant professor for chemistry and also for the sustainability sciences. So that was the path for me. It was pretty direct. Not very many people have such direct experiences. And I think that you don't have to. I mean, there's a lot of things that if I could go back, I would change, and I would probably expand more. Like I find now that I do things that are sometimes unrelated, like to what I do. Like I do things with electronics, and I would have liked to have some kind of formal training on it rather than just like an enthusiast, an amateur on the topic. But it's just a matter of, I think that there are so many choices out there right now. Like, it's just amazing how many career paths there are. The one thing that I find people should be aware of, students that are coming out of high school and deciding a career, is that the more specialized you go in, the less you broaden your horizons. So when you go and you study an environmental career, you are saying that you want to focus on the environment forever. And that may be a way you feel right now, but it not necessarily is how you're going to feel 10 years from now. So I find that when one studies chemistry, when one studies physics, when one studies biology, as opposed to studying, for example, biotechnology or nanoscience, or you don't confine yourself to these little drawers of knowledge that are so, confining. So I guess that my advice is, it's not that the broader the better. You need depth, absolutely. I just find that sometimes these amazing choices that we have, really, are they really promising are they going to deliver what they promise, right? That's one thing that I would like to encourage. And if you have any inclination for science, anybody that is watching us and they have any inclination for science, and you thinking of teaching, becoming a high school teacher or an elementary teacher, if you're really good at it, go for it. Because I find that one of the biggest problems of Canadian society right now is that students are coming out of high school and they're either afraid of science or they can't do math, and it's because of an intimidation that was presented to them in their schooling, either at elementary level or at high school level. And I think that it's because the teachers may not have the tools, and it's because we're leaving the teaching to people that don't necessarily have the desire, the passion towards science that we would like to have in our kids. So if you don't have it, how can you pass it along? So I think that if anybody out there has a love for science and they like teaching, I think that what we most desperately need right now is teachers that can convey that passion for science and for math. Mm-hmm. But again, path is just leave the options open. I think that's one of the main things to keep in mind. Leave as many options open as you can.
That's some great advice and some good insight as well. Thank you so much, Dr. Laredo.
So my pleasure, absolutely.
Great. I'd like to thank you again so much for taking the time to join us. I'd like to thank all our viewers and everyone who asked a question today. It's great to have everyone with us. So that's it for today. Thanks again.